Hi, today I'm talking about LeetCode problem 230, kth smallest element in a binary search tree. What this question asks you to do is find the kth smallest element in a binary search tree. Now, a binary search tree is a data structure such that any node, excuse me, something happened to my screen, such that any node has the properties that its left-hand side is going to be less than it, and its right-hand side will be greater than it. Everything on its left is smaller, everything on its right is greater. So that's a binary search tree. It has these values, 5, 3, 4, so on. And what we want to do is find the kth smallest value. And what it means by kth smallest value, you can think of it as there are k minus 1 values in the tree that are smaller than it. So in their example, they ask you to find the k equals 1 smallest value, and the tree looks like this, 3, 1, 4, 2. So there are 0 values smaller than the one we're looking for, which is of course 1. Nothing is smaller than that. If k was 2, there would be 1 value smaller than that, and that would be 2. There's only 1 value smaller than that, and so on. And the constraints for this are that the number of elements in the tree are going to be between 1 and 10 to the 4th, and k is always going to be valid. So that's useful to know, that we don't have to handle the special case of, well, what if k is invalid? When I was thinking about this, I was mainly trying to think of how can I know if I'm at the kth smallest node, or what does it mean to have k minus 1 things smaller than you? And I think that k minus 1 items smaller than, less than our target. So essentially it has to do with counting the number of nodes in your tree. So if you think of, let's see, we're at a current node, and if the node's left-hand path is equal to k minus 1, then that means there are k minus 1 things smaller than you. Remember, the left-hand path, all those values are smaller than you. So if you're at, if the size or the length of your left-hand path is equal to k less than 1, then the answer is just going to be the value of your node. Because let's say our k is 5. So here, when we're evaluating this node, our left-hand path is equal to k minus 1. There are 4 nodes on its left. That means the kth smallest value is 5. So like that's one possibility. If the size of your left-hand path is equal to k less than 1. Another possibility would be that the left size, or the size of your left-hand path, I'll just call it left size, is greater than k, or greater than. So if it's greater than k, that means you're not at the kth smallest value. There are more than k values that are smaller than you. And if that's the case, if there are more than k values smaller than you, then what you need to do is just move down to your left-hand path and start searching that left-hand path until you eventually find a place where there aren't more than k values smaller than you. And then the third possibility, if it's not equal and it's not less than, k might be greater than the size of your left-hand path. So if k is greater than the size of your left-hand path, then what that means is, okay, the kth smallest value is somewhere on the right. So in this example, if k was 6, we'd know we only have 1, 2, 3, 4, 4 values on our left. So the 6th smallest value can't be in the left branch. So it must be in the right branch. And so we go to explore the right branch, but when we go to explore the right branch, we know that we've already found this many values that are smaller than us. Because when we go to the right, we will have all of these values in the square I just drew be smaller than us. So when we search the right-hand path, we'll reduce k by the size of this rectangle. And so that's basically the logic. There are those three conditions. The size of your left-hand path is equal to k less than 1. Okay, that means we're at the kth smallest value. And we can just return the current value. If the size of our left-hand path is bigger, then we need to explore the left-hand path to find something like this. And if the size of the left is less than k, then we need to explore the right-hand path and reduce k. Okay, let's see what that looks like in code. As I mentioned, one thing we're doing is calculating the size of our structure, of our tree, to know how many nodes do I have on the left and how many nodes do I have on the right. And so to do that, I've just written this recursive function, tree size. I'll explain this part in a minute. But the first thing we just do is say, okay, if the tree we're currently exploring is none, then the size of a tree of none is 0. Otherwise, we're going to calculate the result as 1, so a node that's not none, plus the size of your left-hand branch and your right-hand branch. And that's going to be the result, and then we'll just return the result. So I think that's pretty easy to see. If you have 1, 0, 3, something like this, the size here is equal to 1 plus the size there, which is going to be 1 plus 0 plus 0. So 1 plus 1 plus the size here, which is also going to be 1, 3. That's the basic logic of it. And then the other thing that's just slightly different or slightly complicated is this, which I think of as memoization, which is I'm asking if my node has the attribute size. If it does, then don't even bother to do the recursive calculation. Just return the attribute size from this node. If it doesn't have the attribute size, then go ahead and do that calculation. And when you're done doing the calculation, then create the attribute size and store our result into it. And so the reason for doing this is because you can imagine, we have this binary tree, and we're going to be searching it for the kth smallest value. And part of our search is just going to be asking for the size. And remember, the size recursively calls down each node. And so if we have to say, okay, what's the size of this? Okay, I'm going to explore the left-hand path. What's the size of this? We're kind of recalculating size many times. Every new node we explore, we'd be recalculating size. So this memoization is just a way to store the size of the current node after you've calculated it once, which will prevent you from needing to recalculate it again. And that'll just make the performance of our size function better. But the core function here is the kth smallest function. And what it does is it gets the size of my left-hand path, and then it just handles those three cases I was walking you through on the whiteboard. If the left size plus 1, I guess that's equal to left size equals k minus 1, as I was writing it on the whiteboard. If left size plus 1 is equal to k, that means we have k less than 1 values on our left side. That means we're at the kth smallest value, and we can just return it. If the size of the left is greater than or equal to k, we're going to explore our left-hand path, keeping k, the same way I was explaining to you on the whiteboard. And then the final step is explore the right-hand path, but reducing by a value equal to this rectangle I drew. So that's our left size, all of these, plus the one here that we're smaller than. So we want to reduce k and then search for it on the right-hand side. And so let's see how I tested this. Testing these problems with binary search trees is always a bit awkward because it's not super easy to construct binary search trees, or at least I don't find it to be. But how I tested it is I took their two examples, and then for example number 2, I just tried to find each of these nodes. So I tried to find the 1 smallest, the 2 smallest, the 3 smallest, 4 smallest, 5 smallest, 6 smallest. If I was being more rigorous, I could have tried different tree structures. Like, what about a tree that's just entirely left-hand path or entirely right-hand path? Or what about a huge tree? You know, I probably should have tried the 10 to the 4th size tree, but I just didn't bother constructing that tree. So yeah, I guess that's it. I've seen values for this go as high as 90% or 99%. I don't know why it was slow that time, but yeah, LeetCode, the performance is always a bit of a variation. But yeah, I guess that's basically it. So I guess the main thing I learned from this is the importance of doing that kind of whiteboard session and thinking about it. And just trying to figure out how would you do this, or how should you do this before you start trying to implement code. You know, that was my key takeaway. When I actually started working on this, I wrote some stuff that was pretty dumb in retrospect. I was calculating the size of where are my submissions? I was calculating the size of the whole tree and the right-hand side, and I really didn't need to be doing any of that. So yeah, I guess that's my main takeaway. If you enjoyed this video, let me know by clicking the like button. If you want to see more content in a similar style, go ahead and hit subscribe. Yeah, leave a comment to let me know you're watching. I'm going to try to produce a LeetCode video a day or something like that. But thanks for your time. Bye-bye.